So series capacitor peak voltmeter. Series capacitor peak voltmeters. The last topic from third unit. Okay. So learning objects first we have to considering on principal operation of series capacitor peak voltmeter and the circuit operation and waveforms and various sources of errors and measurement. Okay, these are the different type of concept you have to learn now. So this is called capacitor, series capacitor, so peak voltmeter. Okay, so this method is invented by Chubb-Forstecque method. This method is also called as a Chubb-Forstecque method. So in this method, so we have to measure the peak voltages by using peak voltmeter. This is called the total arrangement is called peak voltmeter. Okay, so the one side is connected high voltage terminal to the high voltage capacitor. So this capacitor handling very high voltages. Okay, one terminal of high voltage transmission line is connected to the here. Okay, so another side is ground. So the diode D1 and the ammeter, DC ammeter is connected in a series. Okay, and parallel with the diode D2. So the diode D1 is conducted during negative half cycle and the diode D2 is connected only positive half cycle. Okay, so this is called C is capacitor and P is called protective device. This is called P is called protective device. So any flashover occur in this capacitor. Okay, there may be a dead short circuit to the entire device. So that's in that case, this divide is protected. Okay, any flashovers occur in this capacitor. In that case, this protective device is protect the entire system. Okay, and so this is the waveforms. So voltage and current waveforms. This is called supply voltage V of t sinusoidal. V of t is equal to Vm sin omega t AC voltages. Okay, peak voltmeters measure the peak voltages. So that is AC. Okay, and IC of t, this is called current. IC of t is called charging current. That is called current flowing to the capacitor. You know well, across the capacitor, current leads, voltage lags. Am I right? And that's why these voltage waveforms start. Exactly for pure capacitor, exactly current leads the voltage by 90 degrees. So that's why the current waveform is starting from here. Okay, and the voltage waveform lags. Okay, so this is the current flowing to the capacitor and the voltage across the capacitor in the supply voltage, that is called V of t is equal to Vm sin omega t. So okay, so in this we have to measure the peak voltages. Okay, so these peak voltages can be measured by using this exponent, total entire exponent. Okay, that may be negative peak or positive peak. Okay, it's clear. So during negative half cycle, diode D1 is a forward biased and it's conducted and measure the current by using ammeter, DC ammeter. And during forward biased, this called during forward biased is only the due to conduct. That means either half cycle is passing through the capacitor is allow the AC. Okay, so this is the different type of waveforms and this is called circuit diagram. Okay, so this is also called as a Chubb-Forstecque method. Okay. You know well, across the capacitor current leads and voltage lags. Okay, this is the some information about circuit diagram, and so we will discuss principle of operation. So then, when a capacitor charges through a sinusoidal voltage, the charging current is given as IC is equal to C into dV by dt. You know well, current flowing to the capacitor I is equal to C into dV by dt. Am I right? When a capacitor charges through a sinusoidal voltage, the charging current is given as IC is equal to C into dV by dt. Okay, this is called charging current. And then second one, if the charging current is limited only one half cycle, okay, if the charging current is limited only one half cycle, then the arithmetic mean of the charging current will be proportional to the peak value of sinusoidal voltage. This is the concept. Okay, if the charging current is limited to only one half cycle, in that case, the arithmetic mean of the charging current will be proportional to the peak value of sinusoidal voltage. Okay, then DC ammeter reads current I is equal 1 by t integral t1 to dt. So by taking the different depths of so time t1 t2, so different type of time periods that is called t1 and t2, the peak. So in between here t1 and t2, like that, here t1 and t2. Okay, can easily understand. So upcoming slides, DC ammeter reads as a current as I is equal to 1 by t integral g t1 to t2 dc into dv by dt. So we'll get like this, I is equal to 2 times of F into C into Vm. This is called peak voltages. Okay, by using that DC ammeter, we have to measure the peak voltages. So in the form of like this, Vm is equal to I by 2 Fc. Okay, the frequency known and capacitance value is known, and so this current measured by using a DC ammeter. Then by substituting here, then you will get peak value of voltages. So Vm is equal to I by 2 Fc. Okay, you know well standard frequency 50 Hz and capacitance value you know well. Okay, by substituting by measuring the ammeter by DC ammeter, that is called PMMC. Okay, by using that you have to measure the current, and by substituting here, then you will get peak value of voltages. Okay, so like this is the principle. So behind the peak voltmeter, inside of the peak voltmeter, so in this way we have to measure maximum peak. Okay, peak value of voltages. This is the concept. Circuit operation. Maximum dielectric strength of the insulator depends upon the peak value of AC voltage. You know well, dielectric strength is depending on peak voltage. Based on peak voltage only, this dielectric material is designed. Okay, the dielectric strength of the insulator is depends upon the peak value of AC voltage. Because of the peak value of AC voltage is very high voltages. Based on that only, this insulator materials could be designed. Okay, so determination of peak value of AC voltage based on the RMS value of will give an error if the waveform is non-sinusoidal. Okay, it's completely based on a non-sinusoidal waveform. If the pure sinusoidal, the input supply is a pure sinusoidal, then we will get the measurement values very accurately. If it is a non-sinusoidal, it is very difficult to measure. So errors present in okay, and the measurement of the peak voltages. Okay, that is the main problem. For only sinusoidal voltage waveforms only, this experiment is suitable. So for non-sinusoidal waveform, this experiment is not suitable. Okay, so because of we will get in errors. When a capacitor changes through the half wave sinusoidal voltage, the arithmetic mean of charging current is proportional to the peak value of AC voltage. I'm already explained. Okay, when a capacitor charges through a half wave sinusoidal voltage by using diodes D1 and D2, so you will get half wave sinusoidal voltages. The arithmetic mean of the charging current is proportional to the peak value of AC voltage. Okay, that's why this method is known as a Chubb-Forstecue method. Okay, they are given a name as these are the two scientists, Chubb and Forstecue. These two scientists are invented this method. That's why this is known as Chubb-Forstecue method. Okay, the diode D1 is used to rectify the capacitor charging current during negative half cycle of voltage. You know well, the D1 used to rectify the negative half cycle voltages, and the diode D2 is to bypass the positive half cycle. It's clear. Diode D1 is only used to rectify the negative half cycle. During negative half cycle, diode D2 is far reverse biased, and diode D1 is forward biased. Only negative half cycle of charging current is passing through the. So this meter, then based on that meter, we have to measure the current, and then positive half cycle, the capacitor, the diode D2 is forward biased, and that positive half cycle discharging through the ground. So only by taking the negative half cycle, we have to measure the voltage, peak value of voltage. Understood? The diode D1 is used to rectify the capacitor charging current during negative half cycle of voltage, and diode D2 bypass the capacitive half cycle. It's clear. This method can be applied to the AC voltages having balance and sinusoidal waveforms in either half cycle. That may be positive or negative. If you are changing the diode connections, D1, D2, reverse magnet. So we have to measure the positive, and negative is bypasses through the ground. Okay. So in case of presence of harmonics or multiple peaks, this method will fail. It's clear. I'm already explained. For multiple harmonics or multiple peaks, this method is not suitable. Okay, understood. So this, for example, for multiple peaks are present in waveform. Okay. So this is the actually this is the voltage waveform. Okay, this is the voltage waveform. Our expecting voltage waveform is like this, but because of harmonics, this is the called this disturbances. Understood? This is called error. This we will get an error here. Okay, false maxima. So we will get so this meter measure the peak one. So that's why we will get an error here also. Actually, our expected waveform. So like this. So for current waveform IC of t. So this is our expected waveform. Okay, But because of harmonics, because of multiple peaks, our expecting waveform is like this. But because of harmonics, so we will get like this. So in between T1 and T2, this okay. So the waveform is so like this matter because of harmonics or because of external disturbance or because of uh, multiple peaks of ripples like this. Okay, harmonics. So our expected waveform is sinusoidal, but because of harmonics, we are getting like this. This is error. And also here also, our expected IC of T, so like this. Okay. So like this. This so red marks here like this. Okay. So but because of harmonics, this negative waveform is shifted to upward direction. There is so like this. This is called error. So because of this multiple peaks, we are getting an error. So this is also error. Okay. Because of this, the diode reverse biased is connecting instead of connecting reverse bias is not conduct. Okay. For negative half cycle only, it is conducting diode D1. Okay. Diode D2 is conducting during positive half cycle. That's positive half cycle. The positive half cycle is bypassed through the diode D2. Okay. Okay. And also negative half cycle diode D1 is conducting. So these are the different type of disturbances we are getting. Okay, because of multiple peaks in a okay the supplies. So this is the errors. It's clear. So next errors in measurement due to multiple peaks. Due to multiple peaks in voltage, the charging current changes polarity within the half cycle itself. Understood? Due to multiple peaks in the voltage, the charging current changes to polarity within the half cycle itself. Okay, so like this. Actually, this is the polarity negative half cycle, but because of multiple peaks, this polarity changes to positive. Okay, actually, this is the direction. Our main direction is like this. Our actual direction of the current waveform is like this. Okay, but because of multiple peaks, the direction of the current is changing because of that errors. Okay, due to multiple peaks in voltage, the charging current changes polarity within the half cycle itself. Okay, that is first one. And second, the shaded area indicates the reverse current during negative half cycle. Okay, the shaded area indicates reverse current during negative half cycle. Hence, this current will be subtracted from the net current. Thus, the voltage peak value indicated would be less there than the actual value. Okay, there is the second one. It's clear. All of you understand it. Then third one, additional source of error is voltage drop due to pre-discharge current in the circuit. Okay, this can be taken care by using a resistance in series with the capacitor such that the discharge time constant is very small as compared to the time period of AC voltages. Okay, by adding some external resistance, we have to increase the time period. Okay, the error due to the resistance will be del V by V is equal to V minus Vm by V, that is equal to 1 minus 1 by 1 plus omega square C square R square. So derivation is not required. The derivation is there in the textbooks. So if you want to go through the textbooks, okay, the error due to the resistance will be delta V by V, V minus Vm by V. So 1 minus 1 by 1 plus omega square C square R square. Okay, this is the error due to resistance will be so like this. Source of error in measurement. First one, effective value of capacitor is different from the rated value of C. Effective value of capacitor is different from the rated value of C. And second one, these are the different type of sources of error measurement. And the reverse leakage current in rectifier. And the third one, multiple peaks in the non-sinusoidal waveform. Okay, variation in the supply frequency. These are the different type of source of errors. Okay, and measurement of peak value. And then finally, summary. So series capacitor peak voltmeter works on the principle of measuring the arithmetic mean of rectified current level. Okay, the current is updated through half cycle charging in series with capacitor from the unknown voltage AC voltages. The non-sinusoidal voltage may be have a multiple peaks causing error in measurement. Okay, you know well, I'm already explained these are all concepts. Other source of error is mainly deviation of capacitance, frequency, and voltage drop due to the pre-discharge current. Okay, so this is for measurement of peak value also.